Today, I am thrilled to have the opportunity to share with you some insights into the fascinating world of two-sample t-test using Minitab. Before we begin, I kindly ask that you take a moment to like and subscribe to my channel. Your support means the world to me and helps me continue to bring you valuable content. Two-sample t is the hypothesis test of the difference between two population means when samples are drawn independently from each other. Statisticians and researchers often use this test to compare the means of two groups and determine if there is a significant difference between them. When we talk about independent samples, we are referring to two distinct groups or sets of items that are not related or dependent on each other in any way. This means that the measurements or data collected from one group do not have any influence or impact on the measurements or data collected from the other group. Let's take an example. You want to compare the daily sales for two different designs of web pages for your internet business. Another example is the gym trainer measured the body fat for a group of men and women who did workouts at a gym 2 times a week for 12 weeks. A healthcare consultant wants to compare the patient satisfaction ratings of two hospitals. The hospitals are independent samples as measurements for the first hospital does not affect measurements for the second hospital. To ensure that your results are valid, consider the following guidelines when you collect data, perform the analysis, and interpret your results. The sample data should be selected randomly. If your data are not collected randomly, your results may not represent the population. Sample data must be continuous. Continuous data has an infinite number of values between any two values. Sample data are from a normally distributed population. Independent samples. Measurements for one observation do not affect measurements for any other observation. As we all know, data analysis is an essential part of decision-making in any organization, and Minitab provides a comprehensive toolkit for statistical analysis for two-sample t-test. The researcher in charge of the new software evaluation project hopes to show that the new software package will provide a shorter mean project completion time. Choose Assistant Hypothesis Tests two-sample t. In Sample 1, enter current software. In Sample 2, enter new software. Under Test Setup, select Is the mean of current software different from the mean of new software? Under Power and Sample Size, optional, enter 15. The report card provides information about assumptions for the procedure being used and contains a list of potential failure modes that can be automatically detected. There are no unusual data points. Because both sample sizes are at least 15, normality is not an issue. The test is accurate with non-normal data when the sample sizes are large enough. The sample is sufficient to detect a difference between the means. This statement holds a profound meaning in the realm of statistical analysis. It signifies the ability of a sample to accurately represent the population it is drawn from, and the potential to identify variations and trends within that population. As many of you may already know, Welch's method is a powerful tool that does not assume or require that the two samples being compared have equal variances. This is a significant advantage, especially in real-world scenarios where equal variances cannot be guaranteed. The ability of the test to perform well with unequal variances, even when the sample sizes are not equal, is a testament to its robustness and reliability. Research shows that the test performs well with unequal variances, even when the sample sizes are not equal. Based on descriptive statistics, the mean for new software is lower than current software. The mean for current software is 335.1 while new software is 262.4. Confidence interval. A confidence interval is an estimated range of values which is likely to include an unknown population parameter. In simpler terms, it is a statistical tool that helps us understand the range within which we can be confident that the true value of a population parameter lies. Now, you might be wondering why this is important. Well, let me tell you that confidence intervals play a crucial role in decision-making processes across various fields such as business, healthcare, and social sciences. By providing us with a range of possible values, confidence intervals help us make more informed decisions and draw more accurate conclusions from data. The confidence interval is generally defined by its lower and upper bounds. This statistical measure is crucial in helping us understand the range within which we can be confident that a population parameter lies. By understanding the lower and upper bounds of a confidence interval, we can better grasp the level of uncertainty in our data and make more accurate predictions. This knowledge empowers us to assess risk, allocate resources, and plan for the future with greater confidence. A confidence interval is a statistical measure that specifies a confidence level, typically 90%, 95%, or 99%. This confidence level is a crucial indicator of the reliability of a statistical procedure. When we use a confidence interval, we are essentially expressing our confidence that the true value of a parameter, such as a population mean or proportion, falls within the interval. The higher the confidence level, the wider the interval, and the more confident we can be in our estimation. For example, if we use a 95% confidence level, we are saying that we are 95% confident that the true value of the parameter falls within the specified interval. Confidence level of an interval estimate 1 minus alpha of a parameter is the probability that the interval estimate will contain the true population parameter. When we interpret a confidence level, say 95% confidence level, it means that if we were to take multiple samples and construct interval estimates using the same method, we would expect approximately 95% of these intervals to contain the true population parameter. How to interpret 95% confidence interval? When we say we are 95% confident that the true value of the population parameter will fall within the x, lower bound, and y, upper bound, interval, what we mean is that based on our sample data and statistical analysis, we can be reasonably sure that the actual population parameter falls within this range. For example, if we say we are 95% confident that the true value of the population mean will fall within the 23 and 28 interval, it means that we are quite certain that the actual population mean is somewhere between 23 and 28. The difference between samples is 72.7. We are 95% confident that the true value of the population mean will fall within the 42.818 and 102.58 interval. P-value. The p-value is a probability that measures the evidence against the null hypothesis, and it plays a crucial role in determining the significance of results in scientific studies. When researchers conduct experiments or studies, they often have a null hypothesis, which is a statement that there is no effect or no difference. The decision to reject a null hypothesis or not depends on the level of significance, alpha. In the world of statistics, the level of significance represents the threshold at which we are willing to accept the likelihood of making a type 1 error, which is the incorrect rejection of a true null hypothesis. In simpler terms, it is the probability of concluding that there is a genuine effect or difference when, in fact, there is none. The choice of significance level, alpha, at which you reject null hypothesis is arbitrary. Conventionally, 0.05 and 0.01 levels are used. In some rare situations, 0.10 level of significance, alpha, is also used. In the realm of hypothesis testing, we often set a threshold value, known as alpha, to determine the level of statistical significance. If the calculated p-value is less than alpha, we have sufficient evidence to reject the null hypothesis, and we can confidently declare that the experimental result is statistically significant at this level. On the other hand, if the p-value is greater than alpha, we fail to reject the null hypothesis, indicating that there is insufficient statistical evidence to reject the null hypothesis. In this case, we must acknowledge that the experimental result is not statistically significant at this level. It is crucial for us, as researchers and decision-makers, to understand the implications of these outcomes. When we reject the null hypothesis, we are making a strong statement about the presence of an effect or a relationship in our data. Conversely, when we fail to reject the null hypothesis, we are acknowledging the limitations of our findings and the need for further investigation. In this example, the null hypothesis states that the difference of completion time between the two software is 0. Because the p-value is 0.001, which is less than the significance level of 0.05, we reject the null hypothesis and concludes that the project's completion time for the two software differ. For alpha 0.05 and sample size of 20, if the true mean differed by 15, you would have a 16.8% chance of detecting the difference. As we all know, the accuracy and reliability of our findings depend heavily on the sample size we use. In order to ensure that our results are robust and meaningful, it is crucial to increase the sample size to 203 for each group to achieve 90% power. By doing so, we can significantly enhance the strength of our conclusions and make our research more impactful. This increase in sample size will allow us to detect smaller effects and reduce the likelihood of false negatives, ultimately leading to more accurate and trustworthy results. 2. Sample t-test is hypothesis test of the difference between two population means when samples are drawn independently from each other. Independent samples are measurements made on two different sets of items. Confidence interval is an estimated range of values which is likely to include an unknown population parameter. The p-value is a probability that measures the evidence against the null hypothesis. When we reject the null hypothesis, we are making a strong statement about the presence of an effect or a relationship in our data. Conversely, when we fail to reject the null hypothesis, we are acknowledging the limitations of our findings and the need for further investigation. I am truly honored to have the opportunity to address you today. As we gather here, I am reminded of the importance of your support to our channel. Your dedication and loyalty mean the world to us, and for that, we are immensely grateful. In closing, I kindly ask for your ongoing support by liking and subscribing to our channel. Your support is invaluable to us, and we are truly grateful for each and every one of you. Thank you for being a part of our community.